Alright, hello everyone. Welcome to this little side video that I put together to hopefully help you see the relationship between how much neurotransmitter binds to ligand-gated ion channels and how strong of a graded potential do we get. Alright, so let's set things up here. This very long axon that you see here, this is going to belong to our presynaptic cell. And then down here we have the whole membrane of our postsynaptic cell. So we'll go ahead and label that here. Alright, so hopefully what you can appreciate is that there is going to be on the postsynaptic membrane a lot of neurotransmitter receptors. So let's go ahead and draw those in here. And each one of them is going to be a ligand-gated ion channel, right? So I'm going to draw 4 of them. So each one has a little binding pocket there for a neurotransmitter to bind. So what we are also keeping track of here is we have a membrane potential graph, and we are keeping track of the membrane potential right here in this cell here. So we're going to stick that electrode right there. So currently it is at its resting membrane potential, right at -70. Threshold is right here at -55, so if we're going to get an action potential eventually in this cell here, we're going to need to get to threshold at the axon hillock. Now, this is not the axon hillock, but just work with me here. Okay, so what we're going to do here is we are going to pretend like this axon terminal is going to release varying amounts of neurotransmitter. So let's start with one neurotransmitter. So not very realistic, but let's say that this axon releases one neurotransmitter. Well, it's going to bind to one neurotransmitter receptor, meaning that as long as there is only one neurotransmitter molecule, we can only possibly open one of these ligand-gated ion channels. So if we say have sodium that moves through this open channel, that is going to cause depolarization of this postsynaptic cell. But we're only getting as much sodium as can go through that one open channel. So we're going to depolarize from -70 here to maybe right there. So we don't really have a whole lot of sodium coming through, so we can't really expect to have a very strong graded potential. Okay, so that was not a particularly strong graded potential. Now let's have another neurotransmitter molecule here in the synaptic cleft. Now we can open a second channel and we can get even more sodium coming in. Twice as much sodium as before, in fact. So this time, this graded potential should theoretically be twice as strong as the one before. So this time we're going to get a bigger depolarization. But as you can see there, once the graded potential comes and goes, it still was not enough to get us to threshold. Okay. Well, this time let's go for broke. Let's again double our amount of neurotransmitters. So we're going to have 4 of them, enough to open all of the neurotransmitter receptors. So now we have, now we have the maximum amount of sodium flowing through these channels, producing 4 times as much depolarization as we saw initially. This should definitely be enough to get us up to threshold once we get to the axon hillock, and once we hit threshold there, we do all the other things that we come to expect with an action potential. We open sodium channels, voltage-gated sodium channels, then we inactivate them, then we open voltage-gated potassium channels to bring us back down. Those potassium channels are slow to close, so we hyperpolarize a little bit, and then the sodium-potassium pump will restore the resting membrane potential. So the whole goal of this little exercise here was for you to see the relationship between how much neurotransmitter is in the synaptic cleft and binding to receptors, and how big of a depolarization, how big of a graded potential do you get. Those things matter when you're talking about what does it take to get an action potential. Okay, so I will go ahead and stop here. Feel free to go ahead and resume the lecture that you paused from in order to watch this, and I will see you later.